Good morning to all my geometry students. Today we will continue with Unit 6, Lesson 6, secants, tangents, and angle measures, specifically Theorem 7 and 8. But before we move on with Theorem 7, there is a concept we need to discuss first, and it's the concept of an external segment. So what is an external segment? An external segment is said to be a part of a segment that is found outside a circle. So that means in this figure we have lines AS and BS. Both of these lines are secants. Line segments CS and DS are said to be external segments. So if we go ahead and we look at our model, we have lines AS and lines BS. As we've already learned, both of these lines are said to be secants. Now, notice here that we have line segments CS and DS, and both line segments are part of the two secants respectively. By definition, line segments CS and DS are said to be external segments because they are segments outside of the circles. Now we move on with Theorem 7, which states as follows. If two secant segments are drawn to a circle from an exterior point, that is, outside of a circle, then the product of the lengths of one secant segment and its external segment, which are the segments we've just defined, is going to be equal to the product of the lengths of the other secant segment and its external segment. Well, there are a lot of words in here, but as we always do, let's go ahead and translate or decode all of these words into a model or a drawing. Theorem 7 is also known as the secant rule. So, in Theorem 6, we talked about the chord rule. So, Theorem 7 is going to refer to the secant rule. So, applying segment 7, let's go ahead and look at the model. First of all, we have a circle and we have two secants. These two secants intersect at point N, exactly at the exterior of the circle. So if we want to apply the secant rule to this model or this illustration, okay, in this figure we have line segments BN and CN, and they are said to be secant segments because they're intersecting the circle at exactly 2 points respectively. Okay? Now, they're drawn to the circle from an exterior point N, which is also the point of intersection of the two secant segments. So based on our theorem, which is the secant rule, we say that the distance from C to N, the product of the distance from C to N, which is this distance, okay, times dN, which is the external segment within secant Cn, is going to be equal to the product of secant segment Bn times En, which is said to be the external segment of secant Bn. Okay? So we also have to notice here that the distance from C to N is going to be equal to the sum of the measures of the distance from C to D, which is 8 in this case, plus the distance from D to N. Now, equally, here we have to see that the distance BN is going to be equal to the distance from B to E, which is 5, plus the distance from E to N. So here we can say that Cn times Dn equals Bn times En. But then we substitute Cn for what? Cn is going to be equal to the distance from C to D plus the distance from D to N. Now equally, the distance from B to N is equal to the distance from B to E, which is in this case is 5, plus the distance from E to N, which in this case is N. Now let's go ahead and use the same example model, and we put it into the following example. So In this case, we have to find the measure of the unknown segment x, which is this one, in the given figure. So our model presents the following. We have a circle and we have two segments, which are also secant segments, okay? And they both meet at the exterior point, which is n. So applying our secant rule, first we establish our equation, which states as follows. It says that the distance from C to N times the distance from D to N, which is the exterior segment, is going to be equal to the distance from B to N, which is the second secant segment, times the distance from E to N, which represents the external segment. So when we substitute our values, Cn, the distance from C to N, is going to be equal to what? 8 plus 6, which is 14. The distance from D to N, which is the exterior segment, is going to be equal to 6. So we have Cn equals 14, Dn equals 6. Now, let's look at the following. The distance from B to N is going to be equal to x plus 5, because x is the value we're looking for. So that means that we use the secant rule in order to help us to establish our equation. So we simply substitute the distance from B to N. We substitute that for x plus 5. And the distance from E to N is going to be equal to what? To x, which is our unknown variable. Now, how do we solve this equation? 14 times 6 is going to be equal to 84. So 84 is going to be equal. On the right side of the equation, we have to multiply x plus 5 times x. So here we use our distributive property, for which x times x equals x squared and x times 5 equals 5x. Okay? So here we have our equation, which simplified as follows. 84 is going to be equal to x squared plus 5x. Okay? So here we have a quadratic equation. We have to set this equation to 0 in order for us to find the positive value of x, which will represent the length from N to E in our figure. So what we do right here, we have 84 equals x squared plus 5x. So what do? On both sides of the equation, we have to get rid of that 84. So what do? We subtract 84 on both sides. Okay? So here, subtracting 84 on both sides, we have that 0 is going to be equal to x squared plus 5x minus 84. So our equation is going to be x squared plus 5x minus 84 is going to be equal to 0. So that would mean that we have a quadratic equation. X squared plus 5x minus 84 equals 0. Now recall, when you worked with quadratic equations in Algebra 1, what do we have to do in order to find the value of x? Well, if we have a quadratic equations, we will find two values for x. We only need one, okay? So the next thing we have to do is we have to set up our t's, in which we have to find factors of negative 84, for which when we multiply those two factors, we get negative 84. But when we add those two factors, we get the coefficient of 5x, which is equal to what? Which is equal to 5, okay? So those factors would be, if we try negative 12 and 7, when we multiply negative 12 and 7, we get negative 84. But what happens when we add negative 12 plus 7? We get negative 5. We're not looking for negative 5, we're looking for 5. So the factors should be, then we change that negative 12 to positive 12, and we change that positive 7 to negative 7. So 12 times negative 7, again, we get negative 84, okay, which is our constant in our equation. That's correct. But when we add 12 and negative 7, then we get 5. And 5 is the number we're looking for, because 5 is indeed the coefficient of x. So then we factor our equation to x plus 12, x minus 7 equals 0. So if x plus 12 times x minus 7 equals 0, x plus 12 equals 0, and x minus 7 is also equal to 0. And there we have our two values of x, which are x equals negative 12 and x equals 7. Since the length of a segment cannot be represented by a negative factor, our answer here is x equals 7. So we choose it because we cannot have negative lengths. Okay? So now let's continue to move on with our sample problem number 8. Okay? Here we have to find the measure of the unknown segment x in the given figure. Again, we have a circle and we also have two secant segments which are meeting at point T, which is located at the exterior of a circle. So this model is implying that the best way in order for us to find the value of x is by using the secant rule. So first we set up our equation in accordance to that rule, which states that the distance from P to T, which is secant number 1, times QT, which is the exterior segment of that secant, is going to be equal to the distance between S and T times RT, which is secant number 2. Now we substitute the values. PT is going to be equal to 10 plus 8, which is 18. QT, which is the exterior segment, measures 8, which is right here. Okay, that's going to be equal to ST, the distance between S and T, which is equal to 16. It's given right here. And here, this 5, this should be an S. So that's equal to 16 times X, which represents the distance from R to T. So then we just plug in our values. 18 times 8, that's 144, equals 16 times X. Okay, so then our equation is reduced to 144 equals 16 times X. We want to find the value of x, not 16x's. So we simply use our division property and we divide by 16 on both sides, and then our value for x is going to be equal to 9. Okay? Now, as we have learned, we have to assess or check our equation. Okay? And we have to check that value of x, which is equal 9. So we simply, again, we plug in our values. PT, distance from P to T, that's 18. Distance from Q to T equals 8. Distance from S to T equals 16, and distance from R to T equals 9, which then you substitute it by 9. So on your left side, you get 18 times 8, which is 144, and on your right side, you get 16 times 9, which is equal to 144. So what do we get? 144 equals 144, and that indeed is a true statement. So by these means, you can assess that your value for x equals 9. Indeed, it is correct. Okay. Now let's do the following example here. This one we already completed. Okay. Now we move on to Theorem 8. Okay. Your Theorem 8 is also called your secant tangent rule, and you can already predict what it's about. It's about a secant and a tangent. So the story is as follows. If a tangent segment and a secant segment are drawn to a circle from an exterior point, again, they are both going to intersect at the exterior of the circle, then the square of the length of the tangent segment is going to be equal to the product of the lengths of the secant segment and also its external secant segment. Again, let's decode all of these words. And let's translate all of these words to a following model. So it all boils down to your circle, to your secant segment, which in this case is PN, and your tangent segment in this case, which is what? Line segment TS. So you have a secant and you have a tangent, and they both meet at the exterior of the circle exactly at point S, which would be their point of intersection. Okay? So your secant tangent rule simply tells you that the square of the distance of TS, which is the tangent segment right here, is going to be equal to the distance of your secant, which is PS, times its external segment, which is QS. Okay? So if we take that into an example, TS, the distance from TS, which is the tangent, the square of the tangent, is going to be equal to the secant times its external segment. So here we have x squared, which is TS, is going to be equal PS, measures 16 plus 4, and that's 20, right? Times QS, which is the exterior segment of secant PS, which measures 4. that tells us that x squared is going to be equal to 20 times 4. Or x squared is going to be equal to 80. Okay? Now, if x squared is going to be equal to 80, here we can see that x squared is going to be equal to 16 times 5, which is equal to 80. Okay? So if x squared is 16 times 5, how do we knock out that square? Okay? What do we do? As we have learned in the past, the value of x is going to be equal to the square root of 16 times 5. But the square root of 16 times 5, okay, by definition of rational equations, we have here that the square root of 16 times 5 is going to be equal to the square root of 16 times the square root of 5. But as we all know, the square root of 16, it's a perfect square, and it's equal to 4. So then our value for x is going to be equal to the square root of 16, which is 4, times the square root of 5. And we can just leave it right there. Okay? Now let's move on to our following and last example. We need to find the measure of the unknown segment x in the given figure. But what does the unknown segment x represent? It represents the distance from M to Q, line segment. But what is the distance from M to Q? It represents the distance of the tangent, okay? So here we use our secant tangent rule, and we can state that the distance from M to Q, we take the square of that, is going to be equal to MR, which is the distance of the secant, times MT, which is the distance of its external segment. So MQ squared equals MR times MT. Now we set up our equation. We simply substitute the values. MQ equals x, so x squared, MR measures what? 6 plus 4, and that's 10. And MT, which is the exterior segment, measures what? Measures 4. So x squared is going to be equal to 10 times 4. Using the same operation we did as in our past example, x squared equals 10 times 4. X equals the square root of 10 times 4. Okay? So that's going to be equal to the square root of 10 times the square root of 4. So the square root of 4, that's a perfect square root. So x is going to be equal to the square root of 10 times 2, or 2 times the square root of 10, applying the commutative property to what? To our product or multiplication. Okay? So here x is going to be equal to 2 times the square root of 10. Okay? And with this, we already finished theorem 8 out of our series of 8 theorems we have in this lesson. So I would strongly advise or recommend you watch your initial video one more time, you work on your problems, and then I'll see you next week. Have a great day. Bye-bye.